Can you guys hear me? You give me a sound check. Check, check.
Yeah, I can hear you.
Thank you. All right. All right. So those of you who are here, my name is Nathan Chapin, and I'm going to be walking you guys through variable frequency drives. It's going to be a little bit condensed, but that's all right. I always give it a little bit of time for people to join us. I don't anticipate we're going to have too many people here, but everyone is welcome. So we'll give it a few minutes. Very much, I like an interactive group if we can. I know it's stinking hot, depending on where you are. And you just go ahead and type in the chat or pipe up if you have a question and have a microphone. That's totally okay. I'll manage keeping us on topic. So we'll give it a few minutes and then we'll get started. I'm going to post some files in the chat. Those files are the resource that we would use for variable frequency drives in year 3, and some of the PowerPoints and my lesson plan. So you guys can have everything all off the
Yes,
get-go.
please.
Yes. What is it?
Yung cake mo, please.
Oh, TikTok.
Yeah.
All right. And everybody, make sure you mute your microphone if you're not intending to say something. Probably best. Okay. I just posted the files above in the chat, so you can download them from the chat. So give that a try, Sheen. So can you not scroll up and see that, Sheen? I just want to make sure, because what I'll do is I'll probably wait. Yeah, okay. You need all the files then? So I'll do this at the beginning and the end of the lesson. So we're about to get started. So I will put them up again now. But if you guys don't have the ability to scroll back, then what I'll do is anyone who joins partway through, you guys are welcome to share this however you guys are in contact with each other. And and then at the end, I'll share those as well too. So those are your files. So this is basically kind of how we're going to start. So this is my lesson plan that I've given to you guys here. And it's just got some basics. But what it does is this is the Siemens Basics of AC Drives, Step 2000. So this is a resource from a manufacturer, and it is very good at covering off what you need to learn about variable frequency drives. However, one thing to note is that wherever it says this MicroMaster and MIDI Master, those are actually Siemens brand of programmable logic controllers. So what you'll notice is in my lesson plan, I reference the page numbers for the book. So those page numbers, you want to stick to those if you are reading through this on your own. Don't know how many of you are going to do that. That is up to you. Just a reminder, as I said already, I do prefer some interaction. So if I'm here for 2 hours just talking to myself, you're going to find it's going to become a little bit dry. So every once in a while, if I ask a question, please chime in, give me a little bit of dialogue back and forth. And without further ado, we are going to get started. So we're going to start with a little bit of terminology, a little bit of physics, I guess. And first of all, you guys all know what a force is. Force is a push or a pull. Really quickly, everybody, does a force always move an object? Let's see what you remember from physics 11. No, good, it does not. So you can push on a wall all you want, you're applying force, it's not moving. If a rotor for an electric motor is in a locked rotor position, it is applying a massive amount of force, but it's not actually doing any work. Torque, and I'm not going to write all these definitions out because I gave them to you. So torque is a twisting force. So the rotational force of a motor as it's driving whatever its connected load is applying that torque through the shaft, through the rotation of the shaft to the connected load, which could be a conveyor, could be a press, could be a chipper, could be all sorts of things. It doesn't matter. So torque is a rotational force. Inertia basically is the characteristic of a body that's in motion wanting to stay in motion. So when we start talking about drives, and we're going to refer to different NEMA rotor characteristics, and basically drives haven't completely done away with that. And when I say drives, just so we're all really clear, I mean variable frequency drives. Okay, just abbreviated. So there's certain load characteristics where if you have a really high, heavy inertia load, the VFD actually needs to be paired or matched with those load characteristics. If it's not, it can fry the motor, it can fry the VFD, it can cause nuisance tripping in your electrical system. So there's all sorts of things. So the inertia of the load is very, very important. Now, speed, we'll go down here. Speed, obviously, we're going to be talking about revolutions per minute. And with speed, and let's just talk about a motor starter. And I'll ask you another question here. Does a motor starter control the speed of a motor? Can we control the speed of a motor with a starter? That is correct. We cannot control the speed of a motor. A starter, all it does is start the motor. It may accelerate the motor. We could be talking about a wound rotor motor where we have access to the secondary windings and we can control the torque at startup, which can control the amount of time it takes for a motor to start, but it's not speed control. So a variable frequency drive, one of the big benefits that it has over any other type of starter is that a variable frequency drive can control the speed, the operating speed of a motor. That's one important difference. Can control the operating speed of a motor. And that can do a few things for us, but we'll come to that in just a moment. Okay, now for speed of the motor, or along, you know what, that we're getting ahead of ourselves already. Let's talk about acceleration and deacceleration. If we can control the speed of a motor, then we can also control the rate of acceleration and deacceleration. And notice that I have abbreviated these here. That is because these, ACC and DEC, they are parameters that can be controlled by the variable frequency drive. And what we mean by that is, under normal conditions, let's say you have almost no load. So we're talking about a fan or a pump. And a fan or a pump doesn't actually generate any load until there's pressure built up, either in the air ducts in a building, if we're talking about a rooftop unit, or until we have water pressure in the pipes, if we're talking about a water pump. So when they first start up, they can start up very, very quickly because the load essentially determines, with a regular motor, the acceleration and the deacceleration rate. With a variable frequency drive, we can set these things specific relative to the amount of time that we want. For example, we can set our deacceleration rate to 10 seconds. So if you wanted to slow your motor and its connected load down in 10 seconds, you can set this parameter to 10 seconds. Let's say we want to accelerate. Maybe it's a really very heavy, high inertia load, and we actually want to take 60 seconds to accelerate. The variable frequency drive will do this. While we're controlling the rate of acceleration and deacceleration, the drive can also control the torque characteristics. So if we go back to torque up here, there are three main torque settings in a variable frequency drive. And this is independent of any manufacturer or anything like that. So there is something called constant torque. Constant torque. I will explain all of these to you in a little bit. There is constant horsepower. And then we also have a variable torque. Yes, this is how I do all of my T's. Don't get confused with that. So there's constant torque, constant horsepower, and variable torque. So while we're controlling the rate of acceleration, we can control all sorts of things about the characteristics of the motor. Instead of with a regular induction motor, simply relying on the connected load to control how long it takes and then the torque curve characteristics of the rotor to determine how it's developing torque. Okay. Friction. I'll include friction and windage here. So friction and windage, when we talk about the efficiency of any electric machine or mechanical machine really, is they have to be able to overcome friction. So any motor is going to have bearings, which will most likely be sealed. And windage simply from, rotating whatever the connected equipment is. The motor has to overcome the force, so it has to do work to overcome these things, which means generate heat, and then whatever the load itself is. And I'll try to use a conveyor and a rooftop unit for most examples, because I think most people understand those quite well, at least in their basic fundamentals with respect to how they work. Okay, now we have work. Work is when we move a force through a distance. So we talked before that applying a force doesn't necessarily do any work. In order to do work, we have to move a force through a distance. And then power. Power is the rate of doing work. So when we talk about kilowatts or horsepower, those are both rates of doing work on the output of an electric motor. And the variable frequency drive is going to control all of these things that we're talking about right now. Now, energy. Does anybody know what the definition for energy is? I know we're going quickly through this, but it is a little condensed. If you want me to slow down, let me know. Or if you want clarification on something, let me know. Okay, so joules is a unit of energy. That's right, Sheen. Now, what is energy, though, in a definition of our context here? Anybody know? Energy is, not quite. I would say heat produced is going to fall more in here. There we go, Jeremy. There's a good fundamental answer. Something that cannot be created or destroyed. You know what? You are correct on that one. So energy, with respect to what we're talking about here now, is the ability to do work. It's not actually doing work. It's not applying a force. It's not doing work, certain amount of work in a certain amount of time, which is rate of power. It's the ability to do work. Now let's find out who pays their own hydro bills. Which one of these things do you pay for when you pay your hydro bill? Force, work, power, or energy? Okay, we have power. Anybody else? Power. It's okay to be wrong. Just toss your guess out there. Okay, we have power and energy. Okay. Okay, we have another energy. We have both. Okay, so I'll explain now. So you pay for on your hydro bill, or whoever pays your hydro bill, whatever arrangement there is there, you actually pay for kilowatt hours. Kilowatt hours is a unit of energy. So you pay for energy on your hydro bill, which means you're paying for the ability to do work. And that should make sense, because if you have a whole bunch of old appliances at home that are more inefficient than the modern ones, hydro does not want to have to pay for the loss because it has a very poor efficiency. So energy is what we're paying for. Now let's talk a little bit about, hang on. We're going to move into, okay, good, I can still see the chat. Just a little bit of AC motor fundamentals. So you would have gone through this in your third year electrical apprenticeship. I'm just going to touch on a few things relative to what we need to know them for variable frequency drive. So first of all, the motor nameplate contains a lot of information for us, and we're going to take a look at one of those very specifically. What I want to point out to you in this diagram is we have our stator windings here. Can you guys see the mouse okay on this? Or should I switch to the laser pointer? Okay, we can see the mouse, okay. So these are our stator windings, meaning that they're housed in the outer frame and they do not move, they're stationary. The rotor, in this case, is a squirrel cage rotor, is in the middle, and the stator windings induce a current and voltage in the rotor, which causes it to spin and chase the rotating magnetic field in a three-phase motor. Very simple. At the end of this shaft, there are fan blades. Those fan blades are responsible for forcing air over all these cooling fins, whether it's a ventilated open frame motor or a totally enclosed motor. The rotor is supported on both ends by bearings. Now, most modern bearings, I'd say 99.9% of them, they are made of metal. What happens when we subject metal to a rotating or moving magnetic field? Anybody? What happens to these bearings in this motor? If I subject a piece of metal to a rotating magnetic field, that's right, Lucky, it heats up. And it heats up because we have an induction taking place in those metal bearings. And those are called, induces a voltage, Tyler, that's right, which causes a current to flow. And that current, of course, is called eddy current. So our eddy currents flow in the bearings. When we have a variable frequency drive, the way that it works is the output induces way more eddy currents into non-current carrying metal parts, which means that the bearings actually have to be oversized and made differently, depending on application. But any motor that's rated for working with a variable frequency drive will have oversized bearings and also an insulating grease, a very specific type of grease that's in those bearings. And of course, we have our connections. So what do you guys think happens? Let's say I take this motor, which is rated at 60 Hertz, and it's a 4-pole motor. And that means it's going to turn, maybe between 1700 and 1790 RPM, which means that this fan is spinning at the same speed, cooling the motor off. If I use a variable frequency drive now to control this motor, and I run it at only 100 RPM. That means that this fan is only running at 100 RPM. So tell me this, is the fan going to be efficient at cooling this motor down? And the answer is no, of course not, right? This is one of the problems that we have associated with variable frequency drives that is easy to overcome. But when we run a motor at a very reduced speed, what happens is this fan becomes inefficient. So there are some inverter rated motors that have a totally separately powered fan here, run on an external circuit. So no matter what speed the rotor is spinning at, the fan is spinning at a speed that is equivalent or capable, we should say, of cooling this whole piece of equipment down. So here we have motor nameplate, and we've got just a few pieces of information I want to talk about here. First, we have the horsepower rating. Now, let me ask you, is this the input power or the output power? Input power or output power? Okay, good. The horsepower rating is always the output power. Service factor is a variable that is used to set the rating of overload protection. Now, variable frequency drive is a motor starter with extra capability, which means that it has to be able to stop and start a motor and provide what's called running protection for that motor. The service factor is a number that we use to determine the overload protection. But what a variable frequency drive will do is it actually will go in. It has a feature called auto tune, and it will electrically measure the characteristics of the stator, through the stator, the rotor, we enter in the nominal system voltage and current, so the FLA of the motor. And the variable frequency drive will do some calculations and determine what this overload setting should be in order to protect the windings inside the motor and also protect the branch circuit conductors, because the overload protection does both. So this number is used in some variable frequency drives. In other variable frequency drives, it's not. The thermal state of those motor windings and of the current going through is calculated in some as well. Now, this FLA right here, is this full load current or just the regular old current when we turn it on? See what you remember about motors. Full load, good. So how much horsepower is a motor doing if I wire it for 230 volts, 3-phase AC? How much current is that motor drawing from the supply? 56.8 amps, right? So if we wire it for the lower voltage, we will draw more current. If we wire it for the higher voltage, we'll draw less current. That's just your power in is equal to power out. Our RPM is given here, and this RPM, and I want to ask you a question on this one right now. We'll just keep rolling. This speed is only achieved when the motor is doing its rated work, which means the motor will spin at 1,750 RPM when it's doing 25 horsepower worth of work on the actual shaft of the motor. So when you start this motor up with no load, you would expect that this speed is going to be much faster. I'm going to change this anyways because my mouse keeps disappearing. Can anyone tell me how many poles does this motor have? We have a rated speed of 1750 RPM. All induction motors work on the principle based on of slip. That means that there must be a difference in rotational speed between our magnetic field and our actual rotor. Let's go back to our piece of paper here. So you'd have learned this formula a while ago in year 2, possibly year 1 or both. And that is frequency is equal to the number of poles, the speed times the number of poles divided by 120. This speed here is called the synchronous speed. So you do have it there, Jeremy, that's right. Yeah, Jeremy and Tyler, that's good. So this is the synchronous speed. So if we transpose this, we'll find that in order to, well, we'll solve for the number of poles, I guess. That gives us frequency times 120 divided by the speed. And the way it works for your speeds is you are going to have either a synchronous speed of 900 RPM, 1800 RPM, and then it goes up and up and up, depending on the poles, with a given frequency of 60 hertz. So this right here, if you did a calculation, it works out close to 4, but the actual answer is 4 poles, which means that there is 4 poles per phase. Okay, so this is one that we're going to be revisiting, and it's one that you guys should know in general for electrical work here. So this motor is continuous duty rated, which means that it will, well, it's rated to run continuously, not intermittently. And it's a rotor design B, NEMA design B rotor. I'm going to show you the differences in those in a little bit. Your connections are also on the motor nameplate. So if you're not sure how to wire it, or if it's a 9 lead or however many leads it is, which would concern me if you didn't know that, but it'll show you how to wire it based on the high voltage connection or the low voltage connection. So these next few slides are basically, they just explain how we get a rotating magnetic field. So we're not going to spend any more time looking at those ones, but understand that the the rotating magnetic field in a three-phase motor, we get that just with the characteristic of a three-phase motor, and that's what makes them as popular as they are. And variable frequency drives, so VFDs, have made speed control of three-phase AC motors equivalent to speed control in DC motors. And that was kind of the goal, because DC motors can have a very, very fine-tuned control. It's what a lot of heavy equipment uses. They have big generators generating DC, and then it's all very fine DC control. So with variable frequency drives, and this isn't, super recent, maybe 25, 30 years ago, we can now control them with the same precision of speed control in a three-phase AC motor than a DC motor. And DC motors, they have a lot of extra maintenance, a lot of extra cost, and so AC motors really are the way to go for industry, for industrial type applications. Anywhere where we use a motor, they make more sense. DC motors are still manufactured though. Okay. Any questions so far? It's all making sense, coming together okay? Okay, good. So when it comes to a motor, and this is one way that we're going to look at it here, is each motor, we have a line voltage applied, and then that voltage is applied to our stator, and that stator draws a certain current. So here's our stator current. And what this diagram is intending to show us is the relationship that exists between the stator circuit and the rotor circuit. And the best way to think of this is to think of it as a transformer. So we know in a transformer, we have a primary side, which would be our stator circuit, and we have a secondary side, which in this case would be our rotor circuit. So the current that gets drawn, there's two parts to the current that gets drawn. There is the magnetizing current. So the magnetizing current is what goes through the inductance of the motor and provides a magnetic link between the stator and the rotor. That magnetic link is what causes rotation of the rotor here. So our stator, of course, has resistance and inductance. So magnetizing current is one part of the current that flows in a motor, and it's generally approximately 30% of the rated full load current of a motor. As you load a motor down, this magnetic link here is forcing the rotor to spin, and it wants to keep spinning as fast as it can. But as we mechanically load that down, it gets harder to spin, so it draws more current. More, in this case, we'll call it working current. And that is the current that's actually flowing in the rotor circuit. And then our link, of course, here is in the flux that is developed between the two. So it is drawn here as connected, but that is a magnetic connection that we're seeing. The resistance in a rotor does change with heat and the current that gets drawn. However, we don't tend to focus on that too much. It's more of an engineering and design type of thing. So this diagram illustrates for us, if we were in a classroom, I would do my left-hand rule, right-hand rule here, just to simply show that the rotor is going to chase the rotating magnetic field in the stator, in the same direction that the stator field is spinning. Okay, so if we have a clockwise rotation in our stator field, we will have the same direction of rotation in our rotor. Now, as it relates to torque characteristics under normal operation, so with a magnetic starter, there's a few different pieces of terminology here. And the first one is a locked rotor torque. This can also be called the starting torque right here. So the way this diagram works is over on the left-hand side, this is zero synchronous speed, which means nothing is spinning. So this would be the instant of startup. The instant you energize the stator, it's going to draw current. It's going to make torque based on the rotor characteristics. That torque will dip as it accelerates. It's going to reach a peak, which we call our breakdown torque. And then we'll settle in somewhere around the, notice this is 100% of our full load torque here, which would be the rated torque of a motor. And the rated torque of a motor is going to give you the approximate speed. So see, this is rotor speed right here. So I would say that this motor, based on this diagram, looks like this line is about 96%, which means it's operating at a 4% slip. So 4% back from synchronous speed, and 100% torque would also be, folks, 100% rated load. So if this was that motor with the nameplate we were looking at first, this would also be 25 horsepower worth of work is where we would experience this full load torque right here. Now we come to this guy. So this is all pre-VFD. This is just going to help us understand how variable frequency drive benefits us and how it also can control the motor. So I'm just going to flip this over here. I'm going to draw this diagram out so that I can mark all over it here. Okay, so here we have percent slip. So at 100% slip here, the rotor is not moving. So this diagram is opposite from the last one that I just went through. This can be 100% torque, 200% torque, 300% torque. That is percent torque. And there's a few things on this diagram, and one of them is current. So this is the current, and if we draw a line straight up, we all know when we start a motor, the instant the stator is energized, we draw a value of current called inrush current. And as the rotor accelerates from 100% slip close to a 0% slip, that this current is going to decrease. So this inrush current will not persist for too long. Now, this is an example of what a torque curve characteristic might look like, depending on whether it was NEMA A, B, C, or D, which we'll come to in a bit. So this is the torque curve. So this right here would be my starting torque. This would be our pull-up torque. This is our breakdown torque. And then, just like in the other diagram, if we followed a line where 100% of our torque reaches this torque curve, that is going to give us the percent slip or the actual rotational speed of that motor. And there's one other thing that's changing here. And that is the power factor of the rotor. So I'm not talking power factor of the motor completely. I am talking the power factor of the rotor. And I want you to notice that right at this line here, and we've drawn it mostly as it should be. There we go. Right at this line here is where breakdown torque occurs. breakdown torque. And it occurs precisely at this point for a very specific reason. At this point, power factor is equal to 70.7%. And we'll come back to that in just a minute. So this generally is about a 25 to a 30% slip where this occurs. Well, let's just go back here. The instant that we apply voltage to our rotor, we're going to have a maximum induced voltage because the rotor hasn't been spinning yet. A maximum induced frequency. So let's talk about the rotor frequency. The instant we energize the motor, it's at a maximum. When the rotor is almost spinning at the same speed as the rotating magnetic field in the stator, the rotor frequency becomes a minimum. As it relates to the inductive reactance in the motor, we know that the resistance is equal to 2 times pi times the frequency, in this case, of our rotor, times the inductance. So right at this point, if I said we have a power factor that's equal to 70.7, do any of you know specifically what type of triangle this is? A power factor that's 70.7. And then we'll tie it in and I'll explain why I'm going through all this. 70.7. What's inverse cosine of 70.7? Inverse cosine, cosine of 70.7. Hang on. Inverse cosine of 0.707. There we go. So inverse cosine of 0.707 gives me a 45-degree angle in my triangle, which means right at this point, right where breakdown torque occurs, we wind up with a power triangle, or you could call it a resistance triangle. It's in the rotor, where the rotor resistance and the rotor inductive reactance are equal. Where these two things are equal, it also means that the in-phase current, or the resistive current, and the out-of-phase current, or the inductive reactive current, are equal. And these occur at different times. You should know that that's the whole idea behind these, representing these triangles and having resistance and inductive reactance, is the current caused by resistance and the current caused by inductive reactance occur at different times. So this causes a current, which causes a torque and a push in the rotor at a certain time to start, and right when this one ends, this one picks up and continues. And that is what causes this maximum amount of torque right here. So let's take a look at the power factor. So the power factor, and again, we're talking about the rotor. Right at startup, can anyone tell me, is power factor at a minimum or is it at a maximum? Okay, we have minimum. Anybody else? I love a good argument. So let's think about it this way. I already identified that the resistance, we keep it the same for our purposes. So if I have resistance is at a maximum, resistance is fixed for both of these. Let's draw this out here. If in the rotor frequency is at a maximum, then the inductive reactance here yes, that's right, Jeremy. If the frequency is a maximum, then the inductive reactance in the rotor is at a maximum, which means that at the instant we start up, the power factor is very, very poor compared to if frequency is at a minimum, the inductive reactance is also at a minimum. Now, the hypotenuse here is the impedance in the rotor. So we have the impedance in the rotor. Notice at startup here, we have a very, very high impedance. And even though we have our inrush current taking place here, this is still the most impedance in the rotor circuit. And this is going to be the least amount of impedance in the rotor circuit. So here's what can happen. And this is getting us into speed control. And then another one of our formulas. And that is how a VFD controls the speed of a motor. And we'll flip back to that in just a moment. How a VFD controls the speed of a motor. And lots of you are probably thinking, well, Nathan, you already mentioned this formula, which is frequency is equal to speed times the number of poles divided by 120. Therefore, we control the speed of a motor by varying, well, we have frequency times 120 divided by the number of poles. So this right here is fixed. We cannot control this. So it should make sense to everybody that if we control the frequency, we control the speed of a motor. Does that make sense to everybody? Of course it makes sense, right? But there's a hazard here. Variable frequency drives do not just control the frequency. They control one more thing, which is going to lead us into torque curves for a variable frequency drive, and then their basic components. So we are getting there, everybody. If we just controlled frequency, if a variable frequency drive only controlled frequency, so if I want to run at a low speed, we have a very, very low frequency. If we go back over to here at what's actually happening in the rotor, at a very low rotor frequency, we have very low rotor impedance. So let's say this is a 600 volt motor and we're running it at a low speed on purpose and reducing this without having everything else involved with running it at full speed. So it's not cooling enough. And it should make sense that if our rotor voltage is at a maximum and our rotor frequency is at a minimum, that's going to give us a rotor current that is going to fry the motor. And I've had lots of students come through. So I teach this course, or I teach a 45-hour course just on VFDs to industry services. So to electricians, technicians, other trades, engineers, and things. And a lot of them come through and want to know, you know, our motors keep burning out and whoever's paying the bills is too cheap to get a better motor. So they put the same motor in. And the reason is because they're running those motors at a low speed. The motors are not inverter rated, but at a low speed, they still draw a massive amount of current. And they're not cooling enough. And they're just continually frying the same motor. It's a definition of insanity, right? Keep doing the same thing and expect different results. So what a variable frequency drive will do, and I know I might be a little bit out of order here with my PowerPoints, but or my lesson plan, but that's okay. Variable frequency drive controls both the frequency and voltage to the motor. This allows for both speed control and torque control. Okay, let's go back and take a look at the lesson plan. See how far off we went here. Okay. So one more formula here, and that is the formula for flux. Now I'll ask you guys another question here in the chat. Flux, what do you think causes an electromagnet to become saturated? Do you think that it's voltage or current? What causes an electromagnet, or a motor is essentially an electromagnet with a revolving magnetic field? And most people think current, Tyler, and part of that is how we teach the strength of a magnetic field in year one and everything else. But the actual flux that's generated in an electromagnet in a motor is actually directly proportional to the applied voltage and inversely proportional to the frequency. So you can kind of think about it this way. The current is going to cause the concentration of those flux lines, but we control the current by controlling the voltage. So the formula here for flux, we're gonna put it aside for now, but we're gonna bring it back again later as it relates to, well, look at this. The VFD controls both the frequency and the voltage to the motor. Well, it looks to me like a variable frequency drive, if it controls the voltage and the frequency to a motor, is actually controlling the flux in that stator. And that's how speed and torque control are achieved, is this statement right here and this formula right here give you the fundamentals of how a variable frequency drive actually works. Okay. Let's go back here, make sure I haven't. Nope, wrong one. Okay, so we went through this formula here. So power factor is improving. Torque goes up to a peak. Depending on the rotor, there might be a bit of a dip, there might not. That depends on the rotor itself. And then the current, of course, starts at a maximum and decreases. So there are 4 different NEMA rotor designs, which I've mentioned a few times now. We have NEMA design A, B, C, and D. Actually, there's a NEMA design E as well. But what you can think of is design A and B. Those are your general purpose motors. So even though we're going to control the torque and everything with a variable frequency drive, the design of the rotor must also be selected appropriately. So A and B are general purpose. Okay, C is going to be a higher inertial load, higher inrush or higher starting torque, but then it's got a lower breakdown torque here. So it's good to get a high inertial load going. And then design D is just high levels of torque on everything else. So this is going to be your beefiest rotor design out there. So these torque characteristics, they do still play out on an inverter or drive controlled motor, but we don't get into them specifically with the theory on a variable frequency drive. Okay, good. I didn't miss too much. So this brings us to the formula that I just went through with you guys, which was variable frequency drive controls the voltage and the frequency of a motor. Now notice right here, and actually, you know what? We're just going to go back to paper for this. Back to the paper a second time. All right. So we'll take a look at this, and then we will take a look at the actual main components of a VFD. So here we have frequency. Here we have applied voltage. So let's talk about now a 600 volts, 10 horsepower, 3-phase squirrel cage induction motor. That's what we're talking about right now. 600 volts. And let's say that this is our 60 hertz in our system. So the output of a VFD is different than most other things that you've seen. And we have a few of those different torque characteristics here. So notice, if I increase straight up here, does it make sense to everybody that I'm increasing voltage and frequency at the same rate? So this would be, you know, well, if I increase voltage and frequency at the same rate, could anyone tell me about the stator flux that's taking place? Yeah, exactly. If we increase voltage and frequency at the same rate, flux stays the same. Now, we'll take a look at this formula, and we're almost done with formulas for this topic. So this again is a formula for the torque developed by an electric motor, and that torque is equal to the constant of the machine. So that has to do with, you know, air gaps and number of poles and the actual physical construction. And then we have stator flux, rotor current, and power factor. So let's look back one more time, and I want you to look at the power factor and the rotor current with me for a second. Do you see how the rotor power factor starts off low and increases to a maximum? And then the current starts at a maximum and then decreases to a minimum? And they kind of have similar shapes to their curves here. So what I would suggest is with that formula, and I'll write it here as well, just so we can make sure we're all getting it here. Okay, it's all in the rotor. Would you agree that the increase and decrease in current and rotor power factor, do they cancel each other out? Mostly, we'll say mostly. Okay, there's, you know, there are some variants, but the current drawn by the rotor and the power factor of the rotor contribute to making this torque curve. Okay, that's what this whole graph really is showing, is the relationship in this formula. So if these two are canceling each other out, then the biggest contributing factor to the torque developed by an electric motor is actually the stator flux. I'll say that again. Stator flux is the largest contributing factor to the torque developed by an electric motor. This is independent of the connected load and everything else. So, by controlling the flux, we're actually controlling the torque. So if we keep the flux the same, and this is decreasing and this is increasing, you know, they kind of cancel each other out. If I have constant flux here, we could make the statement that this is constant torque. And it's measurable, very measurable. So long as we are increasing voltage and frequency at the same rate, that motor is going to make a constant torque, which means there aren't any big dips in starting torque and pull-up torque and breakdown torque. And the translation mechanically is that you're going to have smoother acceleration and better control of your connected load with a constant torque right here. So that's constant torque. Now let's take a look at something called variable torque. So this right here we'll call variable torque. Variable torque. The application for this is pumps and fans. And if we look right when we start off, do you see how frequency is increasing a lot more than voltage? And so that gives us, if we look at this formula, a larger frequency and a smaller voltage, that decreases your stator flux. And that stator flux causes a decrease in torque. So we don't start with a whole lot of torque, but right about this point, now it starts to increase the other way. Now frequency is not increasing as quickly, but the applied voltage is increasing more quickly, which causes an increase in flux, which causes an increase in torque. So the reason why this has its application mainly in pumps and fans is the reason I identified before. When you first turn a fan on in a building, there is no load, there is no resistance, because there is no static pressure in the ducts inside that building being fed from that rooftop unit. There simply isn't any, which means we don't need a whole lot of torque to get that fan spinning and to keep it spinning. But right around this point, and this is very adjustable, by the way, you could have a much smaller belly, you know, in the line, or we could go extreme all the way like an L. As soon as we reach about this point, we're building up pressure, whether that's static pressure in the ducts from a fan or water pressure in pipes from a pump. So now we need more torque to continue to increase the system in that way. So that is variable torque. So we have a change in torque because we have a change in applied flux out of our variable frequency drive. Now we have our last piece of torque we're going to talk about here, and that is constant torque. So we have one more formula to look at. Sorry, I wrote the wrong thing down. Give me one sec. I meant to write constant horsepower. Hang on. Somebody stole my whiteout. Okay. We already did constant torque, constant horsepower. Horsepower is equal to the torque times the speed divided by 52. There are many other formulas for torque. This is just one example. We want to keep it simple here. So notice what's happening. Remember, we drew a line straight up from 60 hertz. So I guess I have a question for you. Variable frequency drive, which is not a transformer. If I have 600 volts coming in and I'm applying 600 volts to my motor, is it possible to increase that voltage anymore? Can we output 1,000, 2,000 volts from a variable frequency drive? And I haven't shown you the components yet, but the answer is no, you can't. So if we have a 600 volt system supplying a 600 volt VFD to power a 600 volt motor, 600 volts is our maximum voltage that we're going to output, or an equivalent 600 volts. So if we increase beyond this 60 hertz, voltage stays constant. And now let's talk about this. I'm going to be going through a manual with you guys, probably mostly next time, maybe a little bit this time. And it has a simulated output frequency of up to 500 hertz. And if you look at this here, let's go with a 4-pole motor. If you applied 500 hertz to a 4-pole motor, we'll quickly do this, see how fast that bad boy is going to be spinning. 15,000 RPM. It's pretty wicked fast. In fact, it's so fast that that motor would probably blow itself apart. So we're not going to run up this fast, but the drive is capable of it. Now, back to this. If voltage stays the same and we continue to increase the frequency, we have an inverse relationship between flux and frequency. As we increase here, flux is constantly decreasing. So let's take a look. If I'm increasing frequency, We know that that's a direct relationship with the speed. And again, if we increase frequency, that's an inverse relationship. The flux decreases by the same amount, which causes the torque to decrease by the same amount. So torque and speed are essentially canceling each other out. This is increasing, this is decreasing. And they do that, and in doing that, that gives us a constant horsepower. So that is constant horsepower. Now, there are different applications for these things. I've identified a few in the lesson plan, and there's a few more in the actual manual that I've provided for you guys, so you can take a look at that. There's also, so this is our three main, torque characteristics. Let me take a look at the time here. Okay, in a minute, we're just going to do a 5-minute get up and stretch, okay? Everybody get up and stretch. There's also such a thing that's called an S-ramp, U-ramp. So when we talk about ramping a motor is essentially we're talking about accelerating or deaccelerating a motor. So if we talk about ramping a motor up, that means accelerating the motor or increasing the speed. Ramping a motor down is deaccelerating a motor or decreasing the speed. So an S ramp can give us a torque characteristic that looks something like this. So we could come across here, go up, go down. And U ramp basically is different ways of creating different U shapes, so joining those 2 points. And again, they're all adjustable. It's all programmable inside the variable frequency drive. Okay. That is a good time for our get up and stretch. So let's back in 5 minutes, which according to the time on here, let's just go with, I'll see you guys back here in 3:44, okay? Back in 3:44, and then we will continue from there. So get up, have a stretch, grab some water. I'll see you back shortly. Okay, can I get a sound check, please, folks? Make sure you can hear me again. Everything turned back on okay? Anybody? Thank you, Tyler. Good to know there's somebody there still. Thank you, Michael. Okay. Yes, good. You're all there. That's wonderful. Okay. So we just jammed in an hour, probably about 2.5 hours worth of material. So before I continue on, I just want to see if anybody wants further clarification about anything, has any questions. So if you got anything at all you want clarified or me to do again, I'll just give you a minute, type that in the chat or let me know. If I don't hear anything in 30 seconds or so, we will just keep rolling. You most certainly can. Normally I would provide these on the Learning Hub. However, I don't have access to half of your Learning Hub because there's 2 fourth-year groups. Go ahead, take a screenshot and I'll slide it up and you can get the rest. No problem. I'll assume that you've got that first bit there. Are they different units? So essentially not, okay, hang on. So let me, today and the 30th. So I'm going to be covering different things each day, Sheen, if that's what you're asking. Yeah, so today is more about a little bit of the history, the theory behind how they work, their main components, and then we're going to get into practical. We're going to go through a manual of a VFD. Now, I'm not going to read it to you, but we're going to touch on all the same terminology and things that we've been looking at here. Just to kind of tie everything to you. And then I'm going to talk about installation and maintenance. And then the problems that VFDs cause in electrical systems. With everything, it's always a bit of give and take. So, you know, variable frequency drives are excellent. We can control the speed of a 3-phase AC motor with very fine precision. However, there are also some disadvantages and they cause problems, a lot of problems. So I will be doing different things each day. So if you want to get full coverage, yes, you have to also be here on the 30th, and hopefully the weather is a little bit cooler then. Just while I'm talking about this, I have another meeting right at 4:30. So right at 4:30, we will be signing off and ending, so you don't need to worry about me going late at this time. Okay. I'm assuming that answered your question there, Sheen? Or maybe I shouldn't. Did that answer your question? Is that what you meant? Okay. Okay, we won't worry too much about this one. I would focus mainly on the constant torque, constant horsepower application. This is just the amount of torque that's available as a motor accelerates and deaccelerates. Okay, no problem. So let's talk about the 4 main components of a variable frequency drive now. So 4 main components. The first main component we have is called a converter. Notice we have 3-phase power coming in, and it looks like we only have DC coming out. So can any of you think of a different name for a converter? Right? Rectifier. That's absolutely right, Tyler. So the first main part of a VFD is called a converter or a rectifier, and its job is just simply to take the 3-phase AC and convert it to DC. Simple. We're going to look at 3 different types of variable frequency drives, and they all accomplish this a little bit differently. The next main component is called the DC link, and the DC link is essentially a filtering section. So inside this DC link, there is going to be capacitors, there's going to be inductors, and their purpose is to smooth out our pulsating rectified DC before it goes to the inverter section. Our inverter section is what outputs our variable signal. So we're changing voltage and frequency here to our motor. So an inverter, as many of you know, it simply takes DC and converts it to AC. And then there's different components that are utilized here. Controlling everything, there's a CPU. Now, VFDs are quite complex in that we could be, have you guys all learned about PLCs yet? Or currently learning about PLCs? Okay, we'll take the from one of you to represent the group. Okay, currently learning, there you go. So when you learn about PLCs, there's all these different, ones and zeros and bits of information. And a VFD is it's a computer, and it can be integrated on a bit level with PLCs and other more elaborate systems. So think about manufacturing. That's more where the home of that degree of control is used. But essentially, we have a computer that is monitoring the rectifier, controlling the inverter section to control the voltage and the frequency on the output, to control both the speed and the torque characteristics of the motor. It is also monitoring the DC link section inadvertently through these two. And then attached to our CPU, there is a bunch of inputs and outputs. So just like with your PLCs, a variable frequency drive has digital inputs or discrete inputs, digital outputs, and then it also has analog inputs and analog outputs. So the same sort of complexity is involved. The difference being with a variable frequency drive, you are setting parameters. You're not building a program from scratch. You do that in the PLC, but the variable frequency drive, you're setting parameters. So here we have a simple speed pot. This is most likely a 10,000 ohm or a 10K potentiometer, which is used as a reference for what the output frequency is. So those are the four main parts and the purposes that they do. So the very first one we are going to look at, this is called the VVI, and I'll write this down here. So the very first diagram we're going to look at is called the VVI. There is also CSI and PWM. So we'll be looking at all three. VVI stands for variable voltage inversion. CSI stands for current sourcing inversion. Just out of curiosity, can any of you hear my 6-year-old throwing his little tantrum? If you can't, we're all good. Okay. And lastly, we have pulse width modulation. So I am going to talk about these two with you. I'll show you the diagrams. Fundamentally, these guys are older tech. So they're not mainstream now. You might find them in a really, really cheap VFD. But almost any drive that you install or come across that's been installed in the last, let's say, 5 to 10 years is a pulse width modulation drive. So this will be the focus of what we're talking about, but I still want to give you a context for these two guys here. So let's go back to our VVI. Okay, so notice we have our 3 sections are shown, 3 of the 4 main sections. We have our converter or rectifier, which for rectifying contains SCRs. So you're probably used to a 3-phase rectifier containing just a 3-phase full wave bridge rectifier made out of diodes. So this is a 3-phase full wave rectifier, but it's made with SCRs. And you'll notice that this one is called the VVI, variable voltage inversion. It's because these SCRs here, they actually vary the voltage onto the DC bus right there. So if you have 600 volts coming in, and if we look at anywhere from 0 to peak, that means our DC link voltage could be anywhere from 0 to 850 volts approximately, because the peak of 600 volts, 600 times root 2, or 600 times 1.414 is about 848 volts. So this controls the voltage. So a VFD controls voltage and frequency. This is where the voltage is controlled. That voltage is filtered through inductor 1 and capacitor 1. And then in the inverter section, this is made out of transistors. Now these are just typical bipolar junction transistors, and they are controlling the frequency of the waveform going out to our motor. Now, can any of you tell me, are these PNP or NPN transistors? PNP or NPN? Has to do with the way the arrow is pointing. Arrow always points to the N type. That's right, Gene. And Tyler and Lucky. Yes, these are NPN transistors. Not that it matters, but again, that's something that, well, now you don't have to review for trade concepts. So voltage is controlled here. Frequency is controlled here based on how quickly they are capable of switching this positive and negative out to the motor. So these switches here, and maybe let's take a look at a simplified version of the inverter section. So we have our DC bus. And the best way to think about all these components is to think about them all just behaving as switches like this. So the transistors, the IGBTs, whatever is doing the switching is essentially opening or closing a connection to a positive or a negative point. So let's assume that's negative, that's positive. Here is our squirrel cage induction motor. This comes to the motor. That comes to the motor. And that point comes to the motor. So we can actually build a 3-phase waveform by switching with this. So that is what those transistors are doing. They're switching the 3-phase power out to the squirrel cage induction motor in this case. Now, this waveform that comes out here, because of how we're switching, it kind of has a tendency to resemble a little bit of a square waveform. Now, that has disadvantages, which is why this type of drive, and same with the CSI, has similar disadvantages, is it causes a current to be drawn. If you think about it, instantly we have a voltage, which means we're going to have a sharp rise in current, but then it's steady, so the current kind of dips and starts up again, and then it goes down to 0, and we get a little transient switch here. So this is actually what the current waveform looks like on the secondary side, so going to the motor. This type of current, we would refer to that as a non-sinusoidal current waveform, meaning that it doesn't look like a sine wave. And in order for a motor to create the torque that it's intended or rated for to do the work that it's designed for, it needs to draw the current in such a fashion that it's most like a sine wave. So whenever we have sharp rises and drops in current, that causes a very similar rise and drop. If we look at this formula in current, that's going to cause a rise and drop in torque because it's not following the same line that it used to in our graph without variable frequency drive control. So what we wind up with is what's called a pulsating torque, not a smooth torque or constant torque so much. And it causes the motor to overheat. It will also cause the motor to behave a little erratically. So you're gonna, if you're familiar with the equipment, you would hear a little bit that it was sounding off. It's going to be drawing a little bit more current from the supply than it normally would. And it's going to overheat and the motor is not going to run smoothly. So this is early days of a variable frequency drive. So here, this is that diagram I just drew out. And this is just demonstrating how different three-phase waveforms, so 3 different waveforms can be produced with these different switches by opening and closing them in a very specified order of succession. And that will give us, well, it looks like we're only showing 2 lines here. So we have line A, line B, but then the line-to-line voltage between A and B is the difference between the 2 here. So what that means is we wind up with a stepped voltage like this, which is a little bit better. This can be referred to as a 6-step method. Sometimes there's an extra little bump in there, depending on the design of the inverter. So it is possible that we could be looking at an output that's intended to simulate this waveform. Let's assume that that's symmetrical AC. And what it does is it goes over, goes up, goes over, goes up, kind of like this. Stepped. And that also causes the same sort of torque pulsations that you can find in equipment controlled this way. So that is the VVI, or variable voltage inverter. This is the CSI, or current sourcing VFD. And notice the converter is the same. So we're varying the voltage onto our DC bus or our DC link in the rectifier side. And then our output, we're using SCRs. So you guys aren't writing a typical test question. I would give you one of these images and ask you to identify which was which. So this uses SCRs both on the front side and the back side, or the rectifier and the inverter. And it has the same disadvantages as the VVI inverter does. Torque pulsation, which causes cogging of the motor. So this is a CSI, or current sourcing inverter. There you go, it's in the chat for you. Okay, I'm not going to talk about this one too much because our focus again is on the pulse width modulation. Now, here we have a pulse width modulation VFD. So notice we have a difference here. In our converter and our rectifier, we have what we're used to seeing. We have a 3-phase full wave rectifier, 3 diodes. Our DC link is the same. We have inductors and capacitors. Some have multiple conductors, some have multiple capacitors. It just depends on the design and the purpose for that VFD. But notice we have a new symbol here in the inverter side. Does anybody know what that symbol is? I'll give you a hint. It is a type of transducer, but not the kind that you learned about in levels 1 and 2. You should have touched it on level 3, but you may not remember. Okay, so actually these ones are still NPM, but that's a good guess, Jeremy. Grant has it. These are what's called IGBTs. I'm going to write that out for you. There we go. New page. So we have IGBTs, and the symbol is very similar to that of a BJT, a bipolar junction transistor. So we have our emitter, and we have our collector, but instead of the base going straight onto that plate here, we have an insulator in between. So IGBT, yeah, just a second, Tyler. IGBT stands for insulated gate bipolar junction transistor. And it has a very distinct advantage that allows our pulse width modulation VFDs to be in existence and to function the way they do. And they can switch upwards of, does anybody have a guess as to how fast an IGBT can switch per second? How many times per second do you think this thing can switch? Oh, it's much faster than that, Tyler. Much, much faster. They can switch upwards of 30 at a rate of 30 kilohertz, which is 30,000 times a second. Did everybody catch that? They can switch 30,000 times in 1 second. Very, very, very fast. Your regular bipolar junction transistors, they can switch up to about 10,000 times a second if you have the control there. But because it's now a voltage controlled device, because of the insulator in here, it can switch much faster than if it were current controlled. And that's simply because current takes time to build. As soon as you throw a switch, you have voltage at the component. Voltage controlled. Okay. So we'll come back to the 500 in a second again there, Michael. That does have a home there. So we have our rectifier, our converter, our DC link or DC bus, and our inverter side. And it's the rate that these can switch that cause or give us a pulse width modulation drive. And we'll come to that in just a moment. So I just want to reinforce here your form factors. Does anybody remember the form factor for a 3-phase full wave rectifier? Okay. There we go. So form factor, you'll remember when you see it, I'm sure, for a 3-phase full wave rectifier. Is this, and I'll represent it a little bit differently. I will simply say that the DC voltage is equal to the RMS voltage times 1.35. So technically 1.35 is the form factor. That is the multiplier between the DC voltage and the RMS voltage. And in the case of a 3-phase full wave rectifier, the DC voltage is actually higher than the RMS voltage. So this formula, this 1.35, if we apply that back to the slide, 480 volts multiplied by 1.35 gives me 648 volts. So this is important to recognize the voltage limitations in a variable frequency drive. So we can have positive 650 or we can have negative 650 with respect to the other terminal. So 650 volts is the maximum voltage that our inverter section can switch. So this is how pulse width modulation works. It always switches. So if we go back here, our IGBTs, or insulated gate bipolar junction transistors, all they're doing is switching between positive and negative values out to the motor. So what they do for one alternation, for our positive alternation, they will switch positive 650 volts. And notice that where I'm in, so this line here is the voltage we're attempting to simulate. So where the voltage is low, we switch on and off, but very quickly. And then there's a bit of a gap. As we work towards the peak of the waveform, notice how our pulses are getting thicker. Right at the peak is where the widest part will be, and then our waveform starts to go down. So we can simulate one alternation. On the next alternation, instead of switching the positive 650 volts, it switches the negative 650 volts, and we get a negative alternation. The controller, in order to determine, if this is supposed to be a 60 hertz waveform, then all of this switching takes place in what you should all know is the time it takes for one alternation at 60 hertz is 8.3 milliseconds. So 8.3 milliseconds this way, another 8.3 milliseconds this way, and that brings us to our negative alternation. So that's how voltage is controlled with the pulses. And then the frequency is controlled with the interval for time between positive and negative alternations. If we wanted to increase the voltage, notice how the pulses are simply wider. In fact, in this case, they appear to be about twice as wide. To get twice as much voltage coming out. So this waveform would be simulating a 600 volt line to line AC voltage. And again, the frequency here depends on the amount of time it takes before the VFD switches its output from positive to negative. So very easy to control the output frequency of a VFD. And the voltage. And again, this is all algorithms built into the equipment. We simply set voltage parameters, current parameters, the amount of time it takes for certain things, and then that's sufficient. But this is what it looks like. Now, we come back to the problem of current being drawn. If we take a look, I'm going to have to go a little bit faster here now. See, we're almost 4:15. Lost my train of thought here. Current is only going to be drawn when there's voltage, or slightly afterwards, because it is a lagging load. So whenever we have a spike, we're going to draw current, and that current's going to go down, and then there's another spike, so we're going to draw current. The current goes up. So this right here represents that current that's getting drawn with another pulse. That pulse is gone, and another pulse. And the width of this pulse is called a hysteresis band. And this can cause the motor to do the same thing, torque pulsations and cogging. The big difference is we can switch these pulses upwards of 30,000 times a second, which means that we can take this hysteresis band and make it very, very narrow. Does that make sense to everybody? I'm going to draw it out in just a second. But the faster those IGBTs switch, the narrower this band gets. And so your current, though it does look like a sawtooth waveform, is much more of a sine wave. So let's take a look at that, and that'll probably close us out for the day. So here, we'll take a look at two different outputs. So in this case, I am going to simulate a waveform that looks like this. And we'll talk about now the difference between two very key pieces of terminology. So switching will be red. So the very highest part, we're going to switch the widest part. And then we switch it more narrowly, and so on here. Same thing on the negative alternation. So the current, so this is our voltage or our pulses, simulating the voltage. The current that gets drawn is going to go up and come down and go up and come down and up and down. And you guys can kind of see that jagged current waveform, not very good. So that will cause the motor to, again, generate more heat, possibly have some torque pulsations. But we can simulate this waveform here differently. You have to bear with me here. All right, we ready? This is what it looks like if you look at it on a scope. So that might seem a little ridiculous, just bear with me. The rate at which the IGBTs switch is called the switching frequency. So let's say that this has, and let's abbreviate this here, switching frequency. So let's say this has a switching frequency that's equal to, oh, let's call it 1 kilohertz. The lower the switching frequency, the more jagged the current waveform. Current. Now let's come over here. And let's say that this has a switching frequency that's equal to, well, let's go with 16 kilohertz, which happens to be the maximum switching frequency in the drive we are going to be looking at shortly. Because these pulses are all so close together and overlapping, what happens is, though the current waveform is a jagged line, you can see how all those little jaggedy edges, when they're happening so quickly, actually make the current look like it's more of a sine wave. And because the current is drawn more like sine wave, the motor acts as though it's just regular current that it would draw. So that is one of the benefits of having a higher switching frequency, is the current that gets drawn is more sinusoidal and your equipment runs better, runs the way that it should. The hysteresis band, which will come back here, just to tie that back. So when it's a low switching frequency, we have a very wide switching or a wide hysteresis band because there's gaps in our switching. They're not overlapping as much. They're not occurring as frequently. Whereas if they occur more and more and more and more, the current maintains a much narrower hysteresis band, which causes the equipment to operate more as it should. So one last thing to compare, and then I'll open it up to questions and we'll see where we're at. Is this kind of making sense to everybody? switching frequency? Okay. If it's not making sense yet, let it kind of sink in, read through that book and see if it does. But again, switching frequency is the rate at which the IGBTs, or we could say the inverter, because they do make up the inverter portion, switches. So the drive that we're going to be looking at next time has a switching frequency of 2 kilohertz up to 16 kilohertz. So we can control it. And it's too hot. I thought you were talking about something else. I was going to ask, what do you think a disadvantage is of having a very, very high switching frequency? And the answer is, well, how much current do you think these things could be switching? It's possible, not even hundreds of amps, think thousands of amps. So drives, just like any piece of equipment, you can have a small 1 horsepower drive, or there's a plant in Delta that compresses gas into it's an LNG plant, compresses it down into a liquid. And does anybody have an idea how many horsepower that the motor is that runs that pump? Anybody? I'll type it in the chat here. 37,000 horsepower. That VFD is the size of the auditorium at BCIT if you've ever been there. Massive, because it's all high voltage. Hydro needs 3 days notice. So the equipment is small, the equipment can be large. So just keep that into perspective as we talk about this. The switching frequency is different than, so we've talked about switching frequency. Now let's talk about simulated frequency. Simulated frequency is the frequency of the output waveform. So if we look at these images here, if the period of the waveform is equal to 16.6 milliseconds, we know that the frequency is equal to 1 over the period. Then the frequency is equal to 60 hertz. So this right here, if this is 8.3 milliseconds, that gives us a period for the whole cycle of 16.6 milliseconds, which means we're simulating a 60 hertz frequency. This right here if this had a timestamp of 1 millisecond, can anyone tell me what the actual simulated frequency is? This right here, 1 millisecond, gives me a period of 2 milliseconds, gives me a simulated frequency of 500 hertz, which is also the maximum output simulated frequency on this drive. So there's 2 different frequencies happening, and this is something that people get mixed up all the time. There's the switching frequency, which involves the IGBTs, and the simulated frequency, which is the time it takes to complete 1 full cycle, or based on the time it takes to complete 1 full cycle. So I'm going to close us off here for today. One of you, does everybody have a screenshot of this one if that's what you were after? Okay, take a screenshot of that one, then I'll post up the other one for you. And I'll stay online till 4:30 unless you all take off, but there's only 5 minutes left. Yeah, and I'll relink those. And again, feel free to share those. So this is the bottom of page the 2nd. Please download and save these files for next time. There you go. That should be all three. No problem, Jeremy. Everybody stay cool. And hopefully we see a little bit of a break coming up here. That'd be nice, eh? All right, best of luck to you in your current topics. The links are in the chat, Sheen. Can anybody else see the links? It should be above where Grant has said thank you. Look up in the Sheen, look up in the chat. There should be a PDF file posted, 3 of them. Scroll up a bit, Sheen. No problem, Michael. Sheen, if you can't see them, send me an email and ask for them, okay? That's probably the best way if you're not sure how to get them off the chat. Do you have my email, Sheen? I'm going to put it in the chat whether you have it or not. Okay, email me and tell me you want the files from today, from your supplemental training. All right, no problem, everybody. We'll see you on Wednesday afternoon when it will be much cooler. At least that's what I want. Okay, I'm ending the session. Bye for now, folks.